We start this video with a quote from Elian Rich of the year 1983. Artificial intelligence is the study of how to make computers do things at which, at the moment, people are better. There exist many types of algorithms to obtain this artificial intelligence, one of which are the machine learning algorithms. Today, we are going to see how these machine learning algorithms learn. The machine learning algorithms are characterized by the fact that you only have to provide them with the data and they learn from it on their own without your intervention. I'm Stefan Pauli, lead data scientist at the Swiss Smart Factory. In a previous video, we discussed an AI or machine learning use case in our Swiss Smart Factory Lighthouse project. Part of this project is to print these drone arms, where the quality goals are not always met, which leads to a relatively high rate of rejects. In this video, we will see how machine learning algorithms work to support a better quality. In the previous video, we talked about the most important parameters for the algorithms. Michael, our responsible for the Lighthouse project, suspects that problem arises mainly if cleaning was delayed too long, which may or maybe not amplified if our laser cutter emits dust. To explain what the algorithms are going to do, let's take a step back and visualize the data that we provide to the algorithms. The time since the last cleaning on the x-axis, the laser usage on the y-axis, and many more like temperature, printing speed, and hundreds of additional parameters on the other axis. As I am very bad in visualizing in 100 dimensions, we will only look at the two-dimensional visualizations. The algorithms, however, can easily work with hundreds of dimensions. When we printed this good drone arm, we had the following condition: almost no laser activity and right after cleaning. As the drone arm was of good quality, the dot is green. Of course, we also measure deformed drone arms, marked with red dots, as for instance the one you see. Now we not only have one good arm and one bad arm, but many of them. Currently, before printing a new drone arm, we don't know if the result will be good or bad, but we know that the value of all the production parameters, time since the last cleaning, laser usage, and all the other hundreds of parameters. This means that we know where the new point, corresponding to the new printed drone arm, is located, but we don't know its color yet, which is why this point is marked gray for the time being. We want to use a machine learning algorithm to predict, given the current production parameters, whether the printing activity will result in good or bad quality, or in other words, whether the new point will be red or green. How such a machine learning algorithm learns, we'll look at next. The first algorithm we look at is the decision tree algorithm. This algorithm asks a question as visualized with the blue line. Is the laser activity above 10%? The aim of the algorithm is to divide the dataset with this question as good as possible in only red and only green subsets. So the algorithm did quite a good job with this question about the laser activity. As we see above the blue line, there are mostly red and below mostly green dots. Now it's not us choosing this question, but the algorithm itself. On the right, you see another representation of the algorithm. A small tree is evolving with the very same question about the laser activity. Based on the answer to the question, the prediction is either red or green. Let's have a look at what the algorithm currently predicts in terms of quality to the arm we want to print now, so the gray dot. The question, if the laser activity is above 10%, is answered with yes, and accordingly, the algorithm predicts red, so bad quality. Of course, this algorithm does not only ask one question, but several. The next is whether the time since the last cleaning is larger than 4 days. And then you see that on the left of the line, there are only green dots, and on the right it's kind of a mixture between green and red. Keep in mind that this algorithm asks the questions not only for the 2 visualized parameters, but for all available 100 parameters. So more questions are asked by the algorithm. Again, one by the laser activity, resulting in only green below the line and rather red above. On the right, a decision tree has formed. Now the nice thing is that once the algorithm constructed this decision tree, we don't even need the data anymore. We are left with the learned decision tree. A new printing order triggers a readout of the current production parameters. These parameters are then fed into the decision tree where all the questions are answered, resulting in a prediction, red or green, or whether the new print job will be of good or bad quality. A nice thing about this algorithm is that it not only gives you the answer red or green, but it also tells you which parameters the algorithm looks at to get to its decision. If you have hundreds of parameters, as in our case, this is a kind of a neat feature. The algorithm tells us which of the many hundred parameters are the most important ones. In our example, this will tell us, for instance, whether the algorithm ranks the laser as a main influencing parameter on the drone arm quality or not. This helps us to decide whether we should do something about the dust from the laser or not. Now in reality, the trained algorithm did not find any special influence of the laser activity on the drone arm quality. Hence, no measures had to be taken. So we trained an algorithm which can predict whether the next printing activity will be of good quality and tell us something about the influencing parameters. One of my favorite algorithms now not only uses one tree, but an entire forest full of trees, for example, 100 trees. The algorithm hence is called random forest algorithm. If we start by taking the data, train the perfect tree for it, take the same data again and train the second tree, we will get a perfect copy of the first tree. And as a result, we'll end up with a forest full of 100 identical trees, and honestly, this would not really help us. So we have to introduce some randomness. For example, we could take 80% of the data, train the first tree, shuffle the data, take another 80% of the data, and train the second tree. Finally, we would have 100 trees, each slightly different, each with its own opinion whether it's red or green. If, let's say, 70% of the trees tend to green and 30% to red, then a democratic majority vote decides on green. As a Swiss, I firmly believe that in politics, democracy leads to better decisions, and in the world of algorithms, I can actually prove it. Of course, there are many different machine learning algorithms out there. All of them have their own special purpose and area of applications. I personally use the presented random forest algorithm very often because it provides quite good results, it's quite broadly applicable, it's quite simple, and it tells you which parameters are especially important for it. So, in my opinion, it's quite a good starting algorithm. In conclusion, we saw 2 machine learning algorithms which learn to predict whether the 3D printing will be successful or not. In case of a predicted poor quality, a user of our 3D printers is warned and advised to clean the printing bed to avoid rejects. I hope I could give you a first insight into how machine learning algorithms learn from data and how artificial intelligence can be created and used in our factories. For those of you who want to learn more about machine learning, we offer a one-day machine learning workshop where you can learn about the algorithms and implement them in a real training system. We use modern data analytics software which simplifies the implementation of the algorithms quite a bit. Different algorithms can be trained and compared by the quality of their prediction. During the workshop, you can collect sensor data on a real training system with a Hilscher IoT gateway, analyze the data with machine learning algorithms, and show the results of the algorithms on the smart light on the training system. Our partner, MyLifeZone, ensures remote access without any installation for each workshop participant to this training system. On the MyLifeZone platform, you will find a large number of technical products for learning and testing. Manufacturers like Hilscher with their IoT gateway can present their real products on the platform to a wide audience and train their equipment easily. Towards the end of the workshop, we're going to discuss additional machine learning use cases from the industry. I'm looking forward to meet some of you in the machine learning workshop. In an upcoming video, we will present a research project of ours where AI is used to make the online courses of the MyLifeZone platform even easier and more intuitive. I'm Stefan Pauli, lead data scientist at the Swissmart factory. See you next time.